Right. Hello, everyone. Welcome. We'll begin in just a couple of minutes and give everyone a chance to log in.
Actually, I'm going to unmute myself. We have a couple of downloads that we sent in advance in the email. It's also in the original registration page. And so if anyone, it's also here. Dave, if you want to throw it in the chat.
Yeah.
We can give everybody a minute or two to install.
Yeah.
And then this will be, the second link is the code that Phil has actually provided that you all will be working on.
There is the chat. Here it is. Pasting those resources in the chat now to all panelists and attendees. Okay, we'll continue giving folks a few minutes here to log on, and we'll get started in a minute. Okay. Well, everybody, let's get started here. I can kick us off. Thanks so much for joining us today for our first hands-on workshop in our series of free webinars presented by Prepare.AI, a St. Louis-based 501c3. Our mission is to increase collaboration around AI and other fourth industrial revolution technologies in order to advance the human experience. I'm Dave Costanero, the technical director. I'm here with my friend and colleague Cindy Teasdale, the executive director. And we've got a couple of distinguished guests here to present with us today. Just a note, we included a couple of files and programs to download. I want to make sure everyone has had a chance to do that. If you don't have the links, you can find them here on the screen or in the chat, as well as the confirmation email you received for this webinar. So feel free to ask questions throughout the session in that chat. This will be interactive. We're excited to hear from you. Now for introductions. Today's intro to our workshop will be run by Philip Milner and Chris Schwozberg. Philip Milner currently holds the role of Advanced Financial Analytics Senior Consultant with Wells Fargo, where he focuses on analyzing and preparing data for financial hedging models. Phil has an MBA with an emphasis in information systems from the University of Missouri, completed graduate work in applied analytics at St. Louis University, and is currently working on a doctorate in data science at California Southern University. He is Chairman Emeritus of the Microsoft Business Intelligence Users Group and an active member of the R Users Group in St. Louis. Christopher Schwozberg currently serves as Technical Lead Senior Data Scientist at Bayer Crop Sciences, where he leverages machine learning and artificial intelligence techniques to solve challenging biological, agricultural, geospatial, and commercial problems. Chris's current focus is on managing development of analytics for high-throughput genotyping labs and integrating automated decisions into centralized data assets. Chris is a graduate of Washington University in St. Louis, where he received a PhD in computational and systems biology, and the University of Illinois at Champaign-Urbana, where he received a master's in bioinformatics and a BS in chemistry. So Phil and Chris, I will turn it over to you guys if you want to present screen and tell us about R. Let's make sure that the...
All right, so here we go. And so I should be sharing my screen, the intro to R, data science in 10 commands or less. And Let's see, hold on. So the plan, why R? We're going to talk about why R, and why not something else. And then doing data science with R and data science go hand in hand. And then along the way, we'll learn the language basics. So why R? R gives you the best payoff for a limited investment. And why can it do that? It can do that because you can look at the language as a set of simple but powerful functions. This is code that other people have written that you can call in a very simple way. And it's also the best payoff because R is an array processing language. That's a little more technically focused, and we'll see that as we go in the presentation. So this is less about computer science and programming, less than other alternatives like Python and C++. And why do that? Well, in a sense, this is about empowering you all using your intuition and your desire to learn and build things. And I like the analogy of like learning the guitar. So if I was going to learn the guitar, I probably would try to learn 3 chords and play a song instead of focusing on learning 30 chords. So you get a quicker payoff, and it's open and accessible to more people. So the bottom line is you get the beauty and the power of the subject of data science without really sacrificing the mechanics. We're going to do a visual, intuitive approach to data science. We're going to focus on using pre-written functions, but we're still close enough to the programming and the mathematics that if you want to do that, if you want to go deeper to that next step, it's there. So you could do all of this with some kind of pre-written GUI tool, but then you wouldn't be able to get to the details. Or you could do it in C++, but then you'd have to write every little thing yourself. So that's one of the reasons why we're doing R today. And the other reason is that it's very accessible to non-computer science people. So if you're in business, or if you're in social sciences or the arts, or you're just an educated consumer, you can do data science too. So let's get right to it. So data science by visualization. So visualizing is intuitive. It gives you a faster payoff, and plus your intuition is in some ways something that you can't do wrong. So it's accessible to you. You know, your intuition can add a lot of value. So let's look at our first data set. Our first data set, there are actually data sets that are built into the R language. So if you've downloaded R and RStudio, which was detailed in the registration or just now, you already have that data set. And what's in that data set? Well, there's 2 variables, the speed of the car and the stopping distance. So this was data that was collected to see how speed and stopping distance work together. And we're just going to jump in right away and do functions. So we're going to, and this is a little bit of a language basic. So a function has 2 parts. There's the function name, which is what you're going to do. And then inside the parentheses, function arguments. You're going to take something, some information, and feed it to what you want to do. And of course, what's our first function? Our first function is visualization. So we're going to, and we'll go through the syntax of this. So we're going to plot, and then inside here we have X signifying X-axis, and equals, which is, we would call that an assignment operator. And it's a very common one in math and in other languages. Inside of functions, you'll see that assignment operator. Different assignment operator. And then we're setting that X axis equal to something. It's equal to the data. And then this $ is a subsetting operator. So we don't want to put everything on the X axis. We want to put just the speed column. And then similarly for the y-axis, assignment, the data, subsetting the data. And what does that one function do for us? Well, it creates this graph. So we look at this graph and we say, well, you know, these points really don't look random. You know, it looks like there's something going on here. It looks like as we move to the right, speed goes up, distance goes up. Move to the right, speed goes up, distance goes up. So we already have an intuition about what's going on here. So now we're going to hop over to RStudio and actually do this stuff. So RStudio is the preferred development tool for R. It's a very good tool and it's free. And we'll just go over the major pieces of it. Up here in this top pane, we have the code. Down below here in the console, we have character output. Over to the right, we have graphical output. Actually, a variety of viewers. We have things about the environment. And so, so that's RStudio. And one of the very first things in any language or technology is getting help. So of course, in R, what do we have? We have a function. So here's the help function, and then it takes an argument. It's kind of a strange argument. It's head. Well, what is head? Head is the name of another function. So you're getting help about some other piece of the language. So we'll run that. We highlight it. We click run. And in this panel, we get a very nice display of what the head function does. It returns the first or last part of an object. So, you know, the top oh so many rows of a data set. And it tells the usage and the arguments and the details. And it's just very nicely done. So, but you can also get help not only about functions or language pieces, you can also get help about data sets. So here's the cars data set. We'll run that. And what do we get? It's the speed and stopping distance of cars, the description, what the columns are, examples of code to run with it, on and on and on. So that's a basic. Another thing that's important is where you're pulling data from and where you're putting data to. So in RStudio, they have the concept of your working direction. And there's a function, if I want to see what my working directory is, I run getWD, and there's no arguments, and I run that. And down here, you can see that it's my C drive and my R Essentials folder. And you could also do that if you go up to session. You could do set working directory. That's another way to do it. Okay, so let's get back to the data. Let's look at the data. So we're going to look at the cars data. It's pretty simple. It's speeds and stopping distances, mostly single and double digits. And then we'll get back to where we came from on the slides. There's our plot. Now, what if we had a slightly fancier function? What if we wanted to see what the best fit line is through those points? Well, then we could use this function, scatter.smooth. You'll notice that the arguments are exactly the same, just like before. So we'll run that. And so we get this curve. This is the best fit line through the points. So it's another kind of confirmation that our intuition about this was correct. But you know, what's a little daunting is that mathematically, curves can have complex equations. And so you could either do this next step before or after, but we're going to take a step back and we're going to look at the spread of the variables themselves. So we're going to do another plot, and this time it's a density plot. And we're going to look at, first we're going to look at speed. So
Hey, Phil?
Yes.
Dave, can I interrupt you just for a second?
Sure.
So I don't see any questions yet coming in on the Q&A or the chat. So I just want to remind viewers, you can definitely do that. And I'm following along with you. And so just to clarify, the file, the webinar intro, webinar_intro_R, is that a little different than the one that you're going through in the presentation?
It is. Good point. Yeah. In order to make the presentation better, I've added some things. I've removed a lot of comments. There are a couple other functions that I've added to it. So, and I'm happy to make this version and the slides available. So that might be something we can do afterwards.
Okay, no, that's good. So just for anyone who has never operated in an environment like this before, I think there's a lot of ways to do any one thing. And so I see that you're copying and pasting things down into the command console on the left. You can also just hit that run button and it'll go to the next thing, skip through comments. Is that right?
My experience of it is that you have to move through it. You have to highlight and hit the run button. That it won't do that for you.
Okay, cool. No, that's good. So yeah, just a reminder to folks, give us the questions as we're going along, and we want this to be interactive, and I want everybody to learn about this. So.
Yeah, for sure. It's all about your intuition, what you can build. So we'll take a look at the speed variable, and when we run that, we get this this plot here. We're kind of hoping for like a bell curve. And this is roughly a bell curve. If it's normal, we get an easier relationship. So let's go ahead and we're going to do the same thing for our stopping distance. And we notice that this one is skewed or pushed to the left. So that might be some reason why we have a more complicated curve. And we can even take a little closer look at the stopping distance variable. This is a box plot. And it shows that we actually have an outlier. So that's another reason why we might have problems. So we're going back and forth between looking at the data, having an intuition, having some sense, trying to have some sense of what's going on. So the next thing that we're going to do is so we have this sense of the relationship, and let's try to measure the relationship. So there is a correlation function, core, and you notice once again that the arguments are mostly the same. So we'll run that. And with this time we get just character output. And down here we see we have 0.806 something. And so what that's showing us is that we have about 0.81 or about an 81% correlation between those variables. So that's a good sign. That's a good confirmation of our intuition. Now we could also do a visual plot of that core plot, and then inside that there's the other function, the correlation function. I'm not going to go into these other arguments at the moment. I just want to show you this visualization. So we do that, and of course we only have two variables, and we have the correlation in the middle, but we have this really nice measure along the side that uses both color and shade to tell us is it positive or negative, and how positive or how negative. And if we had more variables, that might be useful, but we'll get back to that.
Cool.
Yeah.
Hey, Phil, we've got a couple questions. Is now a good time to pause and take them?
Sure, absolutely.
Okay, let's see. So we got somebody says, my version of RStudio allows you to run as long as you're just on the line of code. You don't need to highlight it. So that's just an FYI.
Cool.
So thank you, Larry. And then we got, so Heather is asking, she's getting an error when she runs the plot density cars distribution. The error says, error in plot-new, figure margins are too large. Is that maybe just like a screen size? Does she need to make the size of her figure?
Yeah, maybe so. She can drag, you can drag these panes bigger and smaller. Maybe if she has it squeezed way down low, she has a problem. So all of these All of these panes are adjustable.
Okay. So Heather, let us know if that
She says that worked.
Oh, beautiful.
Yay.
Somebody else says, let's see. Oh, I lost this one. Somebody had a problem getting the run button wasn't showing up, but I think you can go there. There's a menu up on the top. All of this stuff is super customizable, so you can like add and remove and put new buttons and things in. So that's probably in the view. You can configure in the view menu, but I don't know if there's in like file run or edit run or session run. Is there a different, if the button's not showing up?
You know, I'm actually not familiar with that. This is, what I have here is the out of the box unmodified RStudio. So I would think one way to solve that problem is just to restart RStudio.
Yeah. Oh, you can also, if you're on a line and you hit Control Enter, that will run the line as well.
Cool.
So, okay. Let's see. Yeah, okay. So go ahead. We'll keep collecting questions here and firing them at you.
Awesome. All right. So we've done a bunch of interesting things. What if we had an even better function? So this is the chart.correlation function, and let's just run that. Okay, look at that. So we get everything that we've done before with this one function. We get, and some of the things, the spread of the variables is even better because we have both a curve and a histogram. So, and that just kind of brings home this theme of the beauty and the power of R and the quick payoff. So that information, and we're going to go back, we're just going to go back and look at that, what we started with. And so now we have some sense of it. We've kind of measured the relationship in one way. We're going to go back to the slides and we're going to talk about the data science process. Okay, so that's where we're at. And we have data and variables, and we've looked at them, and we have some intuition about the relationships. And we looked at correlation and how to measure correlation. And so now what we would do is we would start picking variables that have high correlations. Now we only have 2 variables, so that's not an issue for us, but almost always it is. And then we're going to create a model. We're going to create some kind of formula or statement that captures the relationship between those variables. And that model allows us to both explain and predict. So we're going to use a very intuitive model today. We're going to use a straight line through the points. And of course, the equation for a straight line is y equals mx plus b. Y, the stopping distance, equals some coefficient times the speed plus the y-intercept. So that's an equation that a lot of the participants are probably familiar with. So then once we do that model and run that model, then we're going to evaluate it and we're going to iterate through the process again. So we're just going to show this slide. This is another way to summarize what we've seen. We have our points. This is our best fit line, our straight line. This is the curve, the more complicated model. And we notice that there's a difference between the two, between our simple model and the more complicated model. So let's hop back over to RStudio and do that. Here's our model, y equals mx plus b. Of course, in R, there's a function, the linear model function. It takes 2 arguments. This is a statement of our model. We're going to take distance, and the tilde means related to speed. And it needs to know what the data is, and the data is the car's data set. So we're going to run this, and it's going to take that equation, our relationship, and it's going to put it to this variable. Now, we have a new assignment operator for that, and that is this less than and hyphen. This is actually the preferred assignment operator outside of a function. So it might be unusual. It's saying take this and put it into there. but that is a language basic. So we're going to go run that. Of course, there's no output from it. And then we're going to use the print command, which the print function is a very generous function. You can look at a lot of different things, and we'll see what we get. Well, here's what we sent in. Here's the coefficients. This is the m, or the coefficient that goes along with speed. This is the y-intercept. So we can take those pieces and we can put them into our equation. And now we have a model for that relationship, right? So the coefficient for speed, stopping distance is the coefficient for speed multiplied by asterisk is multiplication times the speed plus the y-intercept. So we're going to do that. We're going to go ahead and we're going to predict or calculate all the stopping distances from all the speeds. Now, what's cool about this, and what's cool in R, is we're not using any kind of a for loop. We're just going to pass it a whole column. It's going to go through each of those numbers. And that's because, I mentioned earlier at the beginning that R is an array processing language. So that's a feature that many other languages don't have. You don't have to write, sometimes you don't have to write for loops. So we're going to do that. We're just going to push all those productions into that variable. And then we're going to just look at it, see what we get. And here are all our predicted stopping distances. And so we look at this and you're going to say, oh, hey, Phil, so look, the first two, they're the same number and they're negative. How can you have a negative stopping distance? So Phil, your model's wrong. That's right, my model's wrong. As the famous statistician George Bach said, all models are wrong. Some models are useful. So it's not about right or wrong. It's about, does this add any value for us? So that's our next task, is evaluating that model. And so the summary function, you can also do that with a lot of different kind of objects, but it'll give you a bunch of statistics about that object. So we run that and we get a variety of numbers. We get our formula. We get these are called residuals. We'll get back to that. We have our coefficients that we looked at earlier. We have standard error, t-values, and p-values. All those things are important. It's great information. We're going to focus on one particular number. We're going to focus on r squared. And our r squared is 0.6511. What does that mean? That means that our model explains 65% of the variability of that relationship, 65%. So that's something. It's not a lot, but it's something. And we're going to go back to the slides and we're going to take a closer look, a visual look at what that means. Dave, I'm just going to check in with you. Any questions at this point?
I think, there was an earlier question talking about, what is the difference between the equal assignment and the arrow hyphen assignment? You talked a little bit about that. Maybe you could elaborate on that.
Yeah, so the equal assignment operator, that's used inside of functions, but outside of functions, you use the less than sign with a hyphen. So, and I don't know if there's a great technical reason. You can flip that that arrow assignment operator, so you can take what's on the left and put it into what's on the right. And the thing too is, like getting back to why R, R has been around in one flavor or another between 25 and 45 years. So it's just, unfortunately, it's one of those best practice things, I think.
Okay. And so I'm noticing that the interface is a lot like MATLAB, which I used to use at a former job a lot. It looks like the variables and the data all get put into the environment tab up in the top right. What's the difference between a data item and a values item?
Well, I mean, there are different data structures or data objects. So every variable, because it's an array processing language, every variable is at least an array, even if it's just a vector, even if it's just a vector of one.
Yeah.
So I think that's, there are values, and then there are the data structures that those values live in.
Okay.
So, and Dave, I'm just going to say, so if you would keep one eye on the clock for me, because, our co-presenter is going to do some more advanced, in some ways, more interesting functions, and I don't want to take his time.
Yeah, definitely. Okay, yeah, then it looks like we're 12:30 now. Maybe we want to get to Chris at 12:40, 12:45.
Okay, so I'm going to, given that, I'm going to go back to R Studio. So what is R squared? So this is our prediction. This is the actual value. R squared subtracts out what we don't know from what we do know. We don't know 35%. We do know 65%. And so let's get back to R Studio. And I'm going to move a little faster, unfortunately. Okay. So what do? We try to go after the variability that we don't know. And generally, we would do that if we had more variables, we'd add variables. We don't have more variables, so we could transform the variables. We could change them and hope to, by modifying them, to get a better relationship. So we're going to run this transform function. It's got really typical arguments. We're going to run that and look at what we get. This is a function. It's about maybe 15 lines of R that somebody else wrote for us. We get the graph, and we're going to put in our lines, our best fit line in our linear model. And then we have these sliders. So this allows us, people have found out over a long period of time that if you take the data and you put it to different exponents, that you can boil out the relationship. And so we can move these. What we're going to do is we're going to transform the Y, and we're going to move this slider to the left. And as we move it, look at that, our two relationships get closer. And I can use my arrow keys, and I can move it a piece at a time. And somewhere close to 0.5, our lines pretty much are one on top of the other. So what does that tell us? That tells us if we take stopping distance and we take the square root of it, then our simple linear model will give us most of that variability. So it's important, here, I mean, we're doing this all visually. We're not mathematicians, but we get the benefit of all that. So, and then we can look at, we can take that, I'm going to take the square root of the stopping distance, and I'm going to put it into a model, and I'm going to look at that model, and we're going to look at the R squared, and now our R squared is about 71%. So there's another one that's important, the adjusted R squared, but that's more for multivariables. We'll come back to that. So we've done those things, and our other option would be to add more variables. We're going to take a quick look at, there's another built-in data set called MT cars, motor trend cars. And we're just going to load that up, and we're going to look at that data. And that data is types of cars, miles per gallon, and then a whole lot of information about the car. And so we're going to work on the question about miles per gallon. And to do that, we're going to, even this I think is too many variables. So we're going to subset it. And that's another big operator. So you get data, you subset data, and you use data. And these brackets are actually a subset operator. It's rows and then columns. Well, there's nothing in the rows. Nothing in R means everything. So we take all the rows and then these columns. So we're going to load that up. And then we're going to do the core plot. What does that show us? Well, here that shows us along the vertical, we have the variables, and across the horizontal, that shows us in kind of a heat map what all our correlations are. And we could pick out ones that are interesting. I'm going to pick miles per gallon and displacement. We could start modeling, and we can even do our fancy function. And look at that. Look at all that information we get from one function. We get the variables, these intersections, so miles per gallon and displacement. Here's the points, the best fit line on this side of that diagonal, and on the other side, we have the correlation coefficient. So I'm going to pick miles per gallon and horsepower, and I'm going to build a simple linear model. And then we're going to look at that. And we have our R value is 0.6024, 60% of the variability. Let's add another variable, weight, as the highest negative correlation. We're going to add that, so miles per gallon related to horsepower and weight. I'm going to create a 2-variable model. We're going to run that. We're going to look at that. And here now our R squared is about 83% of the variability. So we've taken something that was useful and we've gotten even more out of it. Now this is where adjusted R squared comes in. There is kind of a penalty. You could just keep throwing variables into your model to explain things, but you want those variables, you want to make that a wise choice. So there's a penalty added. So here our adjusted R squared is just a little bit less. So I'm going to pause and check back in with Dave on questions and timing.
Yeah, Phil, that's great. I think we can transition to Chris. There's one question about teeing this up. If you want to send this to somebody, I'm sure there's some sort of scripting that you can put a title and axes labels and that sort of stuff. Is that?
Sure. Oh yeah, absolutely. In fact, what I've done is I went through most of these functions and I stripped out the axes labels just because I wanted to get across, the power and the simplicity of it.
Yeah. So Timothy asked that question about that. Timothy, I think that's one of the powerful things about this. You can just throw in, here's the title, and you can be programmatic, like put those into a loop, like, if you want to like generate a whole bunch of plots and then put in a variable, like here are the names for the 10 of the same plots for 10 different machines or items or rows or whatever.
In fact, what it typically does, there's parameters like this, the X label and the Y label. So you can pass those in. There's a lot. I mean, R is it's built for visualization. So
awesome. Real quick question from me, Phil. The 3 stars on the correlation, is there any significance to that?
Yes. So I think that goes back to, so there's stars, and if you look down here, so there are these significance codes. So another way to look at, you can also look at like, what's the probability you would get that value? What's the probability that it's just pure randomness or that it's something other than randomness? And that's, a lot of people who have taken statistics, they know that people look for, it's not true, but is it true at the 0.05 level?
Okay.
So there are some problems with focusing on that approach, but that's kind of beyond the scope.
Cool. No, that's great. And then last question from the audience here. This can take all sorts of input files, right? CSV.
Oh yeah. And I just hopped over that again, so I wouldn't take any of Chris's time. Let's see. But yeah, and it's as simple as read dot my file type and write dot my file. So right here. So here's the function read.csv. If I had a CSV in the file name and I'm putting it to a variable, and you can read and write different file types.
Cool. All right. Well, let's go to Chris then, I think.
Awesome.
Thanks, Phil.
You bet.
Hello, everyone. That was a fantastic presentation, Phil. I really appreciate that because you set this up very perfectly for me. So let's just go.
Yes, I left out a lot of things for simplicity, and Chris is going to remedy that.
All right. This is not what I want. Can everyone see my my desktop here?
Yep.
Okay, great.
Tiny print.
That's right. I did not want. Everyone can see the PowerPoint. Is that correct?
No, I see tiny print on a
Oh
black.
no,
Maybe a different monitor or something.
I don't want to scare everyone.
There it is.
How about this?
Yep, looks good.
That's great. So Phil was describing what we use as models. And I really wanted to just kind of give a very simple overview around what are we actually doing when we are presenting these models and when you type that model function that Phil was referring to. Really, as Phil mentioned, we're really just creating a line here. And so when we talk about regression, what we're saying is we have a continuous input here on the x-axis, and we're trying to predict a continuous output, just for this example. And so what that looks like is an individual point of your data, and as Phil showed, we had scatter plots, right? So we're showing y versus x. And when we're trying to evaluate our model or our line, all we're doing is we're measuring the distance between the estimated predicted point, which is y, and the actual value that we put in as the input on x. And so what this looks like mathematically is the left-hand side here. So I'm not trying to introduce math to scare anyone, but I just want to show how simple this actually is, because this is the fundamentals of machine learning. The equation that I'm showing here is basically an average. And what is it an average of? Just the average of all of these red lines. That line is just showing what was predicted here by the model, which is this scary WTXI. All that is just describing this line and what our prediction was. And all we're doing is subtracting how far away from this line it actually was. And so we take this, we square that number and divide by the total number of points that we're actually evaluating. And so all it's doing is just summing up how far away from our points we actually, how far away from the line we actually are. And so there are many ways in which you can draw, in which we can create a line. And so Phil showed that one of the models that we were looking at was this straight line here. And so normally we call this ordinary least squares. We also could have some more complicated relationship here in which basically we're kind of walking along the data and drawing a line as we follow the data across the space of X. And I would say this is a pretty good estimation of what the data looks like for these particular data points. We could also create something really complicated. We could draw a very squiggly line to try to fit our data to our model. And so what this would do is we would have very small red bars, just like we saw in the example here. So you might think to yourself, well, of course I want this particular model because the fact that it has the smallest red bars. But what we're trying to do with machine learning and with data science in general is really to estimate what our model is going to do when we see something new. And so, for example, if we had a new data point show up, sorry, I should have highlighted this, but say we had a new data point come up here. In the case where we have a very squiggly model, we would get that new data point pretty wrong. It would be pretty far away from our line. But if we had something that was a little bit more simpler, then we would get that more correct. And so what I'm describing here is really a very simple problem that occurs in machine learning over and over again, But it's very important to understand the trade-offs here. And so when we're talking about fitting our data, fitting our model to our data, I'm describing a problem of fitting. And so on the left-hand side, we would say that this model might be a little bit underfit. It's a little bit too simple. And on the right-hand side, we say that this model is overfit, or basically it's fitting way too closely to our data. But this only makes sense in the context of evaluating something that you haven't seen before. And so this gets me to the next topic, which is really around how do we set up our data to say, hey, this is a new data point. Oh, sorry, skipped one. So how do I say there's a new data point that we're observing? And so the way in which we do this is to split our data into two sets, a training set and a testing set. The training set on the left-hand side is really saying, let's use machine learning, let's use that complicated equation from the first slide and say, let's build what that line looks like. Let's fit the, our model to the data. And then the test set is really, what is my performance on that data set on an example of data that I haven't seen? And so in this case, we're saying, take 3/4 of your data, use it to train your model, and then you have an evaluation on the remaining 25% here. And so I want to now hop over to RStudio and talk about what this looks like in code. And I want to do this in particular with a package called Caret. And we'll talk a little bit more about the pros and cons of Caret and talk about what this looks like. So at this point, I kind of want to pause to make sure that this kind of fits with what Phil had talked about. And if anyone has any questions about this training testing framework in data science.
Cool, Chris, there's no questions on the Q&A or the chat.
Sounds great.
Sounds good to me.
So just real quick, what I should have done when I was doing mine is I should have held back some of the data and trained on part and tested on another part. And that's what Chris is going to fill in for me.
Okay, can everyone see my RStudio?
Yep.
Okay, great. So I'm just going to make this a little bit bigger so everyone can see it. All right, so I just loaded up RStudio, and I will absolutely share this script with everyone after the session. I apologize I didn't pre-share it. So the first thing I'm going to do is exactly what Phil did, which was loading up the library here, and this is called Caret. This takes a couple of seconds to load up because of the fact that it's loading up a large number of other dependent libraries. Another thing is that Phil worked with a data set of cars, which comes with the default R library. So what I'm doing here is I'm loading up a different data set called cars. How do I know it's different? Well, there's 18 variables. In the data set that Phil had, he had 2 variables. This is because the fact that in R, you can have multiple variables with the same name. And if you load up something like dataset cars, what that does is it overwrites the previous dataset that was called cars before. And so now in memory, as you can see in the right-hand corner here under the environment tab, we have a dataset called cars. And so another way that we can look to see that this is different is to look at the summary function and see indeed there are a large number of variables here for this data set. But the main idea behind this data set is that we have an output, which is price, and we have a number of features of this car that we want to be able to use to predict the price. And so you might imagine that how long you've had a car would make a big difference in terms of being able to predict the price, or how many doors it has, whether it's a fancy car or something that's cheaper. And so what we want to do is first, before we start any sort of modeling, we want to be able to split our data into training and testing. And so we use the Caret library to be able to do that, and we run create data partition. So all I did here was run this particular create data partition. And what this does is it gives me an index. So it gives me a vector with which all that is just a list of indices of an array. So I know that's a pretty loaded sentence, so let's go to the help function for Caret. And so if you'll notice here on line 9, I pressed help, create data partition. And so all I'm doing here is I'm bringing up the help function in this right-hand side here, and this is describing the description of this function. And so what we're doing is we're taking y, which in this case is the price, right, which is the output that we're trying to predict. And what we want to do is we want to use 75% of it for training. And that's about it. And so if we want to output what these indices look like, we can just run this. And you see here, we have the vector. I'm just going to make this bigger. We have the vector of indices that we have here. And so we're using 1, 2, 3, skip 4, 5, 6, 7, 8, 9, 10, skip 11, 12, etc. And so all this is doing is this is saying for the examples of cars that we have, we want to hold some of them for training and hold some of them for testing. And so let's do that.
Chris,
so
there's a question, Anthony, in the Q&A. This is probably a lot of detail to this question, but any general guidelines on like how to split the data into train versus test?
Absolutely. We're going to talk a little bit more about that. So I'm going to hold on that question. So there are many, many different paradigms in terms of splitting your data in training and testing. It is project specific, but I will hopefully give you some guidelines on that as we move through this a little. And I have a slide around this too.
Great.
I have 7 minutes, so I'm going to try to get to most of this as quickly as possible. So what we want to do is first use these indices to select the rows that we want to use for training, and then select the rows that we want to use for testing. Great. And so now we can see, using the nRow function, which is describing the number of rows that we have for training, we have 604 for training and 200 for testing. And that's all based on the percent data that we're using for training versus testing. Usually this 75-25 or 80-20 split, if you're just using a training set and a testing set, and it's like you can do this randomly, this is usually a good, good rule of thumb. And so then what we want to do is we want to train our model, right? And so this is definitely what Phil was talking about when he showed all of the awesome data that we had around your correlation with your data. And so really what we want to do is we want to fit our model as well as we can. And what we're going to use is a linear model, which means that all we're doing is we're saying, give me the best line that we can draw through our data. And the way that we're doing this is using the train function through Caret. And this is really the power of Caret, which is that it has about 237 different functions, different machine learning algorithms that you can use by just defining this right here, method. This parameter here equal to whatever the tag name is in Caret, which is the information is here. You can find any machine learning function that basically you can think of and call it all the same way, just using train. And so it makes it very simple to say train and then given any method that you possibly can think of. And it's really great to be able to use all of these functions to compare each of these models together. And so as we showed in the PowerPoint, you could draw a line or you could draw a really squiggly line. So the way that we describe what we're trying to predict is right here, which is the first argument, which is price tilde dot. And so all this means before we had, I apologize, Phil, we had speed, I forgot. We had two variables that we're looking at. And so these are variables that are in the cars data set. But all we're saying here is that we want to predict price as a function of all of the other variables in this data set. And that's all the dot means there. The other fancy thing that we can do with Caret is we can perform pre-processing. So Phil mentioned some transformations that we can make to the data. These are all things to really just standardize our data so that each of the variables that we have as predictors all are sort of on the same scale. So when we look at the cars data set, you know, we're trying to predict price. That's right here in the first column. And we're trying to predict it as a function of mileage, as a function of cylinder, doors, cruise. If you notice, miles here is on a very different scale than many of the other features that we have in the data set. And so we want to remedy that, and we want to use a couple of different pre-processing functions here. Caret ties all of this together to make this very easy and very simple as just an additional parameter in your training. So let's train this model. And that's it. It's done. So let's check out what did this do. So we have an R squared of 0.904, and this is pretty good. And so I mentioned before that we want to be able to make models that are a little bit more sophisticated in order to not just have that straight line, but have maybe something a little bit curved that can better explain the data. And so let's try this with something that's a little bit more complicated. The only thing that I changed here is the method, okay? And so let's run this particular method and let's see what this did. Not a whole lot. So this is now 0.905. And so it slightly improved it in terms of our model fit. Let's try another more complicated function. And I know I'm just kind of running through these, but I mostly just want to get to the point. This is a function called Lasso, slightly different. And this has 0.904 is the best one. So what I'm showing here is basically different ways to run different models very quickly and compare them pretty easily. Another way that we can perform this is this training testing is with a different type of holdouts. So we described training and testing as splitting this into two different data sets. I just briefly want to talk about what if we split this a number of different ways. So I described previously the training testing framework in which we took 75% of the training data set and then tested on 25% of the data set. Another way that we can perform this training is through something called cross-validation. And so in this case, we chop up the data into 10 smaller data sets of the training, take 9 of them, and then test internally on 1. Why do we do this? Because of the fact that we don't want to overfit to this testing data set. We want to be able to use this testing data set as a ground truth for our actual performance when we deploy this to our business partners or use this in our research. This cross-validation framework really helps us be able to do that. Helps us be able to say with confidence that when we see something new, it truly will be that performance. And we can be very certain that we haven't looked at our data or looked at our testing data set too often. If you have even more data, say more than the 804 examples that we had in the CARS data set, we can do this cross-validation on the training data set. You could have an intermediate validation set, and then you could have a testing data set that you basically held out for a very long time and never looked at that. And so the main point that I want to say in this section is really around being able to use Caret to evaluate a large number of these functions. Makes it really, really easy for you to just blow through a lot of these different functions, use cross-validation to understand what all of your subtle differences are in your data to make sure that you're fit just right. And then you can go ahead and you can test using your best model that you chose there. And so I could just pause there. I know that we're at time, but I can also take questions or I can keep going through material as well. So.
That's great stuff, Chris.
Thanks.
So one question is that, can Caret automatically choose the best model or function?
Yes, yes, it can. And this was another point that I wanted to talk about, which is that when we're choosing the best line here, we are choosing parameters of our model. Parameters are the things, when I say W here, these are the parameters that are learned during training. So this is, I could draw a really wonky line here and it wouldn't be very good. All the red bars would be very large. There are other types of inputs that we can have to our functions before the function actually runs. These are called hyperparameters. And so as I was clicking through in RStudio, there were a number of different models that I was running. And these different models have inputs before the function actually trains. And so these are the hyperparameters that we need to specify before the model is actually able to learn anything. Caret makes it very easy to not only compare between different models, but it also makes it extremely easy to compare between different hyperparameters and allows us to choose the best model amongst many and the best hyperparameters for that particular model.
Okay. Let's see, so once you've produced a successful model, how would you then deploy it into a functioning application outside of R?
That's a great question. So I believe you're referring to what happens when we have testing, right? So I think that question is a little bit specific to the use case, but if you do some research on R Shiny apps, I would say that this is probably the best deployment, the best self-deployment. And what I mean by that is you as a data scientist being able to actually share your data with a broad community such that they can interact with your model. So an R Shiny app is basically a very sophisticated way to do what Phil did with the, I'm sorry, Phil, can you remind me of the function you called?
For like correlation plot or even more sophisticated plots, those types of things?
I believe it was called manipulate, is that right?
Yeah.
Yes, great.
Yes.
So for the manipulate function that Phil shared, an R Shiny app is just a very complicated and more, I would say, more robust way to basically play with your data, play with different models, and play with the output. Oftentimes, R Shiny apps are called dashboards. and dashboards have become extremely popular in the past couple of years. You can see examples from New York Times, 538. There's a lot of different websites that use dashboards in order to not only just communicate data, but oftentimes there's a lot of data science that's actually baked into these dashboards. And it's a really nice way for data scientists to be able to communicate the results to people who need to use these insights from the data.
So I guess, Chris, to expand on that a little bit, when you deploy to production, like, this question sounded to me a little bit like, okay, maybe I'm Netflix and I built a new recommendation engine, a machine learning thing. It's a support vector machine or a linear regression or whatever model it is. To deploy it to the production, those are often going to be a Python or a, other type. Do you see R running in? So you described like some graphical user interfaces, more research stuff, still like drilling in that side of thing. But like, is R ever really used to run and deploy like a high speed, high volume model in production, in a product or a platform?
Yeah, once again, it totally depends on the application. So you mentioned something like Netflix. I would argue that it really depends on the application and on the company. So let's take an example of Netflix versus a company like something I'm very familiar with, Bayer Crop Science. Bayer, we have 3 divisions. We have crop science, pharmaceuticals, and consumer health. We have a wide variety of products, and each of those products have their own different cute data sets. Netflix has a very streamlined product that they produce. I'm pretty sure they've killed their DVD shipping, and it's completely online content. So their delivery production system looks a lot different for their one product as a recommendation, and they probably have engines that are set up around those recommendations that has a very streamlined deliverable. And so probably the production engine is specific to whatever team is responsible for making sure that content is pushed out to its consumers appropriately. At Bayer, for example, we have examples of R in production. We have examples of Python in production, Go, tons of languages that you possibly, many things you can think of, and it's really specific for the application.
Okay. And so, there are some of these like frameworks that serve as a translator between languages like Onyx. Can you take an R model, translate it into Onyx, and then load it in Python? Have you heard of that happening?
So there's an RPy2 package in Python in which you can run Python or R code explicitly from Python. I don't think that there's a need for an intermediate translator there. Yeah.
So question for me on, so I'm more of a Python guy, and I'm kind of
me
just,
too.
Okay. So this was really helpful for me. I wonder, I Stack Overflow the heck out of things and, look for code on, Kaggle or GitHub or Stack Overflow. What are some similar places where you can find R code and scripts and help?
So there's the R bloggers site, which is extremely useful, especially for finding helpful hints. That's a really good resource. If you're looking for an introduction to data science in general for R, there's the Introduction to Statistical Learning book, which is extremely useful, which will give you kind of a mathematical flavor to understanding what each of these functions are actually doing. And then also I heavily recommend, and this is more recently, the Tidyverse, which is a way in which you're better organizing your data, your code, makes for very clear communication of your workflow, and really helping to organize all of these many functions and modules that you use in R. And I actually think that it is something that R very recently has done better than Python, in my opinion. Even though
I want to jump in here just for a second and follow up on what Chris said. So Tidyverse was written by a gentleman named Hadley Wickham. And so if you're going to remember one name from the presentation for our additional resources, it's Hadley Wickham. You know, he was an academic statistician, and now he's the chief scientist at our studio. He's created a lot of these things. He has whole books and courses that are interactive and online and for free. You know, so that just follows up on what Chris said.
Awesome. Yeah, no, that's super helpful. All right, so we're going to throw the our resources slide up here, and we've got these links, and we can send them out as well in the follow up to this. But there's all kinds of resources. So you know, our blogger, Tidyverse, and then a bunch of stuff in and around St. Louis. You know, the data science community is robust and growing quickly in this area. So would encourage you to check out some of these meetups, some of these organizations and areas. I think we're about out of time here. So, you know, Phil and Chris, I'll give you guys, you know, the last word. Any closing comments or thoughts on this today?
Yeah, I would just say use your intuition and go build something. You know, that we need everybody in there. And R has a great community. That's one of the big pluses of it.
Absolutely. Use your passion to build something. You know, it's really tempting to just take an example data set from as a starting point, but really apply data science to whatever you're interested in using to change the world. It's a very powerful tool, and it's really low cost to get in there and get your hands dirty.
That's awesome. Thanks so much, gentlemen. Thanks to all the panelists. Check out our information coming. We have a web seminar, another free web seminar coming up in mid-July. So we'll be sending that information out soon. We'll follow up with this, with these resources and links. You can also check this out. This video we'll put up on our YouTube channel. You'll be able to find that and past recordings from our webinars and conferences in past. And follow us on Facebook and LinkedIn. Have a great day, everybody. We'll talk to you later. Thanks.
Thanks so much, Chris and Phil. Have a great day, everyone.